Hello, students. So this is part 2 of chapter 12, and we're continuing with structure determination. So we've already talked about mass spectroscopy. In this video, we're going to cover IR spectroscopy, and there's another area of structure determination, that's NMR spectroscopy, that we'll cover in chapter 13. So first, I'm going to just talk a little bit about the electromagnetic spectrum, talk about IR spectroscopy, really interpreting a spectra, because that's what's key for you to be given a spectra, identify what are some key peaks there to help you figure out the structure of an organic molecule. And then we'll just really focus on just what different functional groups, what type of peaks that those give. Okay, so we're in the business of looking at IR radiation in this section because that is the area of the electromagnetic spectrum that has an energy that corresponds to energy that can be absorbed by molecules as they stretch and bend. So this is where the infrared region is. Visible is here, where it's light, we can actually see as color. Higher energy, it's to the left, UV, X-ray, gamma, etc. So as we go to the left, we get higher energy, higher frequency, and that actually corresponds to a shorter wavelength. So electromagnetic radiation, it has what's called duality. So it has dual properties. It can behave like matter, like photons delivering a packet of energy, or it can have this wave-like behavior and move as a wave. The speed of a wave can be determined if you know the wavelength and frequency. Multiplying those gives the speed. We're going to be looking at essentially a modification of frequency. If you rearrange this equation, you get frequency is the speed of light over wavelength. And in the IR spectrum, what's reported on the x-axis is something called a wave number, which is actually wavelength divided by speed of light. So it'll be not wavelength, frequency divided by speed of light. So it'll be 1 over wavelength. But basically that just comes out as a number for you on the spectrum. And just to make sure you understand, a type of radiation will have a certain frequency, as I just showed you on that electromagnetic spectrum. That frequency corresponds to the energy of a photon of that light. So a little packet or bundle of energy from that photon. And that's related to the wavelength, but basically there are very specific energies associated with a certain radiation. And that's what we're going to be looking at in terms of what a molecule can absorb. Organic compounds exposed to electromagnetic radiation can absorb energy of only certain wavelengths. So that's key for us because what we're going to do with an IR machine is basically change the wavelength and just look at what wavelength is absorbed by that particular molecule. And from that, we can get an absorption spectrum. The key piece of this is, again, what I said, IR radiation can cause a molecule to bend or stretch more vigorously. Molecules are moving around. There's always some level of motion or energy, even if it's really slight. Everything's always in motion or has some energy associated with it. So bonds are stretching, they're bending, molecules are spinning in space. And basically, we are going to irradiate a molecule and see if we get more absorption, more bond stretching. Just to calibrate you how that compares with other radiation, say if I shine a light of UV radiation, and there are other types, an atom can absorb that energy, but maybe that's not going to correspond to being a stretching frequency, but basically that's a higher energy photon. So that's actually enough to move an electron in that atom to a different level, different orbital, and even possibly eject an electron from the atom. So what we're in the business of is looking at infrared energy. And molecules can stretch. There are different types of stretching, symmetric, anti-symmetric. There's bending, in plane or out of plane bending. So just imagine, for example, a tetrahedral molecule, and all those atoms are balls on a spring. Just think how they can all move and bend and stretch. So I want to correlate this with something that is relevant in terms of something happening globally, and that's greenhouse gases causing global warming. The reason I bring this up here is because the greenhouse gases are causing global warming because they are absorbing IR radiation. So just to give you an overview, the Earth is heated by the sun. We know that. Energy from the sun warms the Earth, but a lot of that radiation is radiated back out into space. However, there are some greenhouse gases, such as carbon dioxide, that are in our atmosphere, and they end up absorbing that energy that's supposed to radiate back out to outer space, and they trap that energy in the atmosphere here. That can then go ahead and be re-emitted in other directions and basically cause an increase in the temperature over time, definitely having impacts on climate change and causing global warming. So what's interesting is carbon dioxide does absorb a peak wavelength in the IR spectrum. That's why carbon dioxide is a problem. So there's bending, there's wagging of the CO2 molecule here. And if the frequency of the radiation, this IR radiation, matches the vibrational frequency of the CO2 or other molecule, then that radiation will be absorbed. So just to tie this in with something else that you may have noticed during one of your labs is these sort of bond vibrations, they can change the dipole moment of a molecule. Because if you have a polar molecule, you're bending, stretching, you're, amplifying that. But also, if you have a nonpolar molecule, look at this, carbon dioxide is nonpolar, but it's a three-bodied system, meaning there are three atoms. So if I bend it, I make it asymmetric. So it can have this momentary dipole. I point that out because these types of bond vibrations change the dipole moment. This is characteristic of IR absorption. So sometimes when you look at IR spectrum, you may be looking for a type of bond frequency, bond stretching frequency, but it's absent. And you may have seen that with diphenylacetylene because that molecule is nonpolar and there is no dipole bond, bond dipole as there is with CO2. So you don't see that, that's absent, and that's not going to be shown or appear in the IR spectrum. The other thing is some other molecules are not going to absorb in this IR range, and that's why they're not going to be greenhouse gases. We aren't going to see any of that with molecules like O2 or N2. So as I mentioned, the greenhouse gases, they'll absorb the IR radiation. They can later transfer that energy in collisions with other molecules or just later emit that energy that was absorbed. Overall, less energy leaves the atmosphere than should have been emitted back to space. So just to wrap this up, carbon dioxide is a big offender, and that's why there's such a push not to burn fossil fuels. Fossil fuels are hydrocarbons. Anytime you burn a hydrocarbon, that's called combustion, and you always make carbon dioxide as a product. So that's why that's such a big offender, and why the world is trying to go towards alternative energies, electric, solar, geothermal, wind. Okay, back to our regularly scheduled program. This is an infrared spectrometer. You may have seen this or used this yourself already. And you put a sample here on top. This is a diamond plate, and you close down on the sample. Basically, there's an IR source that's going to give you the different wavelengths of the IR radiation. It's going to hit a mirror and a beam splitter that can separate those out and go through your sample. Again, certain wavelengths of light will be absorbed if they match that vibrational frequency of the molecules stretching or bending, and then that'll be detected. by a detector and spit out as a spectrum on the computer. So here's our IR spectrum. On the y-axis, we have percent transmittance. On the x-axis, the wave number, which is 1 over lambda. Lambda is the wavelength. And percent transmittance is basically a way for you to visualize. If you're at the top at 100, that basically says the molecule's not absorbing anything different than what like your reference sample is absorbing. So it's basically nothing's happening. But if you see peaks going down towards 0 transmittance, it means it did absorb a lot of that radiation. So these are going to be key diagnostic peaks for us as we look through different spectra and confirm identities or help differentiate between different molecules. So here we see a CC double bond. I'm going to point out others as we go through this. Sometimes IR spectrums can be difficult to interpret just because molecules are complex. There's a lot of different bonds that are similar. So some of the disadvantages generally used in pure samples of fairly small molecules. There are other spectroscopy that you can use slightly impure and be able to tell the difference. The advantage is that if you do have an authentic sample, you can use that as a unique identification. There's a whole fingerprint region to the IR. But as you've seen in your interpretation of IR spectra in the lab, it's not necessary to interpret the whole spectrum. A lot of times we're just looking at key bands, key diagnostic peaks. Here's a sample table. You also have one from your lab manual. And I'm not going to go through all of these. We'll go through them in the next few slides, but come back to this. Use this as a reference. Here are hydrocarbons, halides, alcohols. Alcohols, you have an OH and a CO. So there's something in the 3000 range or 1000 range. Aromatic rings have something specific. Amines, the CO carbonyl peak is very strong and is around the 1700 region. This is really key to helping you identify compounds with carbonyl compounds. Carboxylic acid has a carbonyl group here, but it also has an OH attached. This number is slightly lower than an OH attached to alcohol group, just a normal carbon. Let's just first break down the hydrocarbons, alkane, alkene, and alkyne. Let's do this visually. Here's an alkane, hexane. You see these CHs. So this is a region where you have CHs. This sort of CH or C double bonded, sp2H or SPH. So notice that as you see from this first spectrum, you're in this kind of 2900 region. As you go to an sp2 carbon, it pulls out of this blob here, and you get a more defined peak around 3000. If you have an alkyne, that CH bond frequency will be even further out around 3300. So those are key diagnostic peaks to help you determine whether or not you have a double bond or triple bond. The other thing is you have that C double bond or C triple bond stretching frequency. That shows up here, so around the 1600s for the C double bond C, or further out past 2000 for the alkyne CC stretch. So those are key things to look for. Know the basic regions. Towards the left, you have a single bond stretching motion, so NH, OH, or CH. These will have very specific shapes too. This region is unique because you have your triple bonds, and then this region here are your double bonds. This is a fingerprint region. It's kind of hard to isolate and identify things here, but a lot of times you use it for additional confirmation. Let's just practice. Here's something you might have to do. Distinguish between, how would you distinguish between the following isomers? You have an alcohol and an ether. So look at those formulas. You have an OH in the alcohol, but you don't have an OH in the ether. You only have a O bond. So both have CO bonds. So the key distinguishing feature is the OH. You're going to look for that. It's going to be strong and broad in the 3300 region. So if I give you a spectrum like this, these have the same molecular formula, but they're constitutional isomers. How do you know which is which? You look for that distinguishing feature. If you have the OH, you have the alcohol, ethanol. If this was absent, you could conclude you would likely, if those were your only two options, you likely have the ether. Okay, here are some key functional groups. Alkanes I already talked about. Alkenes we talked about as well, looking for those key peaks in the 3000, 1600. Look at these though. If you have a double bond outside of the, kind of not internal so much, but like a CH2 at the end, these are low. You guys saw that with beta pinene. You saw that like at 880. So that's another key peak to look for. Alkynes, the internal one, 2000 region. If you have a terminal alkyne, you'll see that 3300 peak show up as well. Aromatic compounds. You guys have been looking at some spectra. You guys have looked at aromatic rings already. There's a range you've been asked to find and identify peaks here, 1600, starting at 1450 here. The 1660 to 2000, this is the overtone region, and this is what it looks like. It's not a big defined peak. It's small little peaks here. The CC stretch in this 1450 to 1600 region, these are an example here of what you would see. And then also you might see your sp2H stretch in this region. Alcohols and amines, they're very distinct. They have very high wave numbers in the 3000s. The amines are slightly lower than the alcohols. I need to show you visually what this looks like. Can you tell the difference? You have this broad OH. We just saw that with ethanol, right? And here, same again with ethanol, broad and strong. Look at the Amine NH. It's not as intense and it's a sharper, less broad peak. So there is some hydrogen bonding involved here. That's why we do get some of this broadening. But basically know the difference. OH is big, this big well. Sometimes it goes all the way down low as well. That's going to be key for you to identify an OH, which again could be an alcohol or could be a carboxylic acid. The other really key peak to know is a carbonyl peak. A CO double bond stretch is roughly in the 1700 region. And you can have, there's a big range here. It's a one big peak, but sometimes it's lower or higher than 1700 because maybe there's resonance, maybe it's tied up in a ring. I'll give you some examples. So an aldehyde is generally 1730, just straight aldehyde here. If there is a potential for resonance and delocalization of electron density, then you observe a lower frequency. Ketones are very close, 1750. Normally, if it's tied up in a ring, there's ring strain, so it's a higher frequency. If there's resonance, it's lower, even down to the 1690. Esters, I show an example here. Again, this carbonyl peak, it's a strong peak. And for the esters, it's similar range as the aldehydes, around 1735, with resonance it's a little bit lower. The other thing is for the ester, you have that CO peak. So you see CO stretches here, kind of around a little past 1000. So let's just practice, and this will be this last part of the video. I'm gonna give you two spectrum here to look at. One of them is of acetic acid with a carboxylic group. The other is of ethanol. Correctly assign them. So pause this, take a look, and make your decision. Okay, hopefully you picked ethanol as the left one. Both of these have OHs, right? So you should see this broad OH well, and both of them are there. You might have noted that this one for the acetic acid, which is B, is slightly lower, closer to 3,000 versus closer to 3,500 in the ethanol. But the key thing you really should have been looking for is whether or not you have a carbonyl group. So if you have acetic acid and you drew out this molecule, it's a methyl group attached to a carbonyl, CO double bond, and that carbon is attached to an OH. This is the key defining difference. So look for that. Also, you may pick up both have CO bond, so that's not a key feature, but this will tell you. And it is a strong peak. That carbonyl one is strong. Okay, that's where I'm going to end today. The next time we talk, we'll talk about NMR spectroscopy, where we actually look at different types of hydrogens on a molecule.